Hello everyone, welcome back. Today we're going to be talking about proofs using the SAS or side angle side congruence theorem. So what is the side angle side congruence theorem? Let's just review briefly what that means. It means that if there are two sets of sides that are congruent, and also the angle in between them is congruent, then that means the triangles are congruent. And so in this situation, it's telling us that AB and DE are congruent, so these two are the same. Also, it's telling us BC and EF are congruent, so those are the same. And also these two angles, angle E and angle B, are congruent as well. And so if those three criteria are met, that means the triangles overall are congruent, right? Meaning that automatically the other side lengths and the other angles are congruent too. So here's an example of how we could use this to prove that two triangles are congruent. It says, example 1, prove that ABC is congruent to CDA, given that BC is congruent to DA, and that BC is parallel to AD. So first thing I'm going to do when writing a two-column proof is I'm going to write out my givens, and I'm also going to mark them on the diagram here. So what do we have that's given? The first thing that was given is that BC is congruent to DA. And that's very useful, right? Because the three criteria we need to meet are two sides, right? Two pairs of sides, and the angle in between them. So we already have one pair of sides already given to us that we didn't have to do any work to get. The other thing was that BC and AD are parallel. And my reason for both is given, right? It's that both those things were given to us. So now we need to figure out how we can prove that another set of sides is congruent, and also the angles between them are congruent too. So the reality is there's not really a way at this point to prove that A, B, and C, D are congruent. We don't know if that's true or not, presumably yet. However, AC is a shared side amongst both ABC and CDA, and AC is certainly congruent to itself. How do we know that? We know that because of the reflexive property, right? The fact that any side length is congruent to itself. So there we go. There's the second side proven. Now we just have to prove that the two angles in between those two sides are congruent as well. So we need a way to prove that this angle, BCA, is congruent to CAD. Now, is there any theorem we know that would say these are congruent? Well, yes, there is, right? The alternate interior angles theorem states that when we have alternate interior angles and the lines are parallel, right? When we have parallel lines in a transversal, then the alternate interior angles are congruent. And so therefore, we can use alternate interior angle theorem to say that these two angles are indeed congruent, right? So we may not have directly used the fact that BC and AD are parallel. However, this was a key piece of information, this right here, because we needed it in order to then make the conclusion that the angles are congruent, and that is one of our three criteria. All right, and now that all three of our criteria have been met, right? We've met criteria 1, which is this one here is criteria 1, that the set of sides are congruent. Then we have criteria 2, another set of sides is congruent. Criteria 3 is that the angle in between those sides is congruent. That means, therefore, by SAS, or side angle side congruence theorem, we can apply that and say that ABC is congruent to CDA. Now, it's very important before we apply this congruence theorem that we make sure we have all the criteria met. That's the most common mistake I probably see as a teacher teaching this course, is that students will go to SAS congruence theorem too early. They'll try to use this theorem without actually having proven all the things that need to be proven first in order to use the theorem. If we go back to the theorem, it says that this is only true if these three criteria are met. So it's important that these three criteria are met first, and then we can apply the theorem. Okay, let's try another example. Given that C is a midpoint of AE and BD, prove that ABC is congruent to EDC. Okay, so before I get into the actual proof here, I want to talk about fundamentally how come this is true, right? Why would it be true that that these are congruent? Well, here's the thing: these two angles are vertical angles, and so they must be congruent. And then we also know that these two must be congruent to these, and this must be congruent to this, right? Because C is a midpoint. And what does a midpoint mean? A midpoint means that each of the sides, each of the parts of it is an equal part, right? If it's a midpoint, it directly cuts any segment directly in half. And so the length of those segments is congruent. Okay, so that's fundamentally why this is true, for those two reasons. Let's write that out in a formal way. So very first thing I'm going to write out for this one is that what is given is that AE, or C, is the midpoint of AE and BD, all right, because that was the only thing that was given to us. The next line I'm going to write is I'm going to write that angle DCE, oh, it's hard to see that, sorry about that, let's zoom out a little bit. Yeah, angle DCE is congruent to angle ACB, and that is true because of vertical angle theorem. The fact that they're vertical angles. Then we can also say that AC is congruent to CE because of the definition of a midpoint, right? What is a midpoint? A midpoint is something that separates the two parts of our segment directly in half, so therefore the two halves must be congruent. Also, for the same reason, by definition of a midpoint as well, it is also the case that BC is congruent to CD. And now we can apply our SAS congruence theorem, right? Because we proved that these angles here are congruent. We proved these angles are congruent by vertical angle theorem, so that's a yes. We proved that these two sides are congruent, and we also proved that these two sides are congruent. So since we've proven all three of these things using either what was given or definitions we knew and theorems we knew, we're then able to say by SAS congruence that ABC is congruent to EDC. All right, well, that's it for SAS congruence theorem. There are other congruence theorems like SSS, AAS, ASA, and also for right triangles, HL for hypotenuse leg. So there are other ways to prove something's congruent that we'll go over in the future.